Okay, so without further ado, let's get going on our lesson. And let's just do a little bit of a warm-up, a recap from what we did on Tuesday. And let's see what you can remember from Tuesday. We've got here a fair dice is rolled once. List the elements of the sample space. Pop it in the chat if you know what the elements of the sample space is. What is the elements of our sample space if we roll a dice? Remember, the elements of the sample space are the things that can happen. There we go, Boniwe. There, the Watobians are waking up. 1, 2, 3, 4, 5, and 6. Wonderful. So those are our sample space elements. Nice. So what is the probability that you will get a 6? Just pop it in the chat. What is the probability of getting a 6? It's 1/6. Yeah, one of the possible 6 outcomes. And what is the probability of getting an odd number? Pop it in the chat. And remember to simplify fractions. Odd number will be 1, 3, and 5. That is indeed 3/6, but we need to simplify it to a half. And then what is the probability of getting a 7? That is 0. Yes, of course, because there's no 7 in our sample space, because there's no 7 on a dice. And what is the probability of getting more than 2? Simplify your fractions, everybody. I see 4/6, but you got to simplify. The probability of getting more than 2 is 4/6, because you can get 2, 3, 4, 5, 6. Sorry, more than 2 does not include 2. Let me take that away. And that is 4/6 or 2/3. Simplify. And then less than 10. What is the probability of getting less than 10? That is 1 or 100%. You can only get a number less than 10 on a dice. Good stuff. Okay, last one in our little warm-up round. A spinner alongside is spun. List the elements of the sample space. Pop it in the chat. So here's this little spinner. It's got blue, pink, red, green, and you can spin that arrow and it can land on one of those colors. So the elements of the sample space are blue, green, pink, and red. There we go. Well done. So what is the probability of the spinner landing on green? 1/4. Nice. And yellow? 0. That's it, because there is no yellow on our spinner. Okay, right. Okay, so let's go on to something new that we're going to learn today, which is this idea of relative frequency. So this morning I had some toast, and as I was eating my toast, I dropped it. So my toast had some jam on it, and the other side obviously had nothing on it. But when I dropped it, I thought, okay, it is going to land on either the jam side or the non-jam side. Okay, so if we can assign probabilities to that, Ms. Coco, what do you think? Jam side, non-jam side, landing on one of those sides. What do you think is the probability?
I think it would land on the non-jam, on the jam side more.
Okay.
But I mean, at the beginning, it's still going to be like a 50-50, right? Because, you're not sure how it's going to land. But
yes. So technically speaking, we can say, theoretically speaking, we can say it's half and half or 50-50. What do you guys think? If you drop your toast, what side is it going to land on, the jam side or the non-jam side? Put it in the chat. Let me see. Chloe May says jam side's heavier. Jam side because it's of the weight. Seems like
It's
Hey?
like that tiny little bit of jam you put on the toast is enough to change the whole weight of the toast. I'm not sure. I don't know.
I think we could get quite scientific here about the jam and the way it's applied, and I mean all these different factors. But because I'm a nerd, I thought I'm going to conduct an experiment to see what actually happens. So, oh, Cecilia's saying the jam side because of the density. But in any case, I decided to conduct an experiment. So I dropped my toast 25 times because I wanted to see if I keep doing it, which side is going to be favored more. Is it going to be the jam side or the other side? Shira says, ma'am, please don't do the experiment. Yeah, we're not going to do it now. It's done already. Ma'am, so much mess. Notice how the girls are like, too much mess. But in any case, in this experiment that I did, it landed with its jam side up 16 times. Okay, so it's just a silly little experiment. Who knows if I even really did it, but let's pretend I did. Okay. So we can say that the probability of the toast landing with the jam side up in my experiment, I did it 25 times, and 16 of the 25 times it landed with the jam side up. Okay. Now we can write that as a decimal and as a percentage. So as a decimal, this is going to be 0.64. And as a percentage, we times that by 100, and that gives me 64%. Okay. And this situation is called, or this experiment that I've done with these numbers, that is called the relative frequency. So if we look back, we kind of said, technically speaking, theoretically speaking, ignoring sort of all the complicated science involved with weight and density and stuff like that, there's a 50-50 chance of it landing either on the one side or the other side, jam side, non-jam side. But when I conducted this experiment, it came out that it's actually about 64% for my experiment. Okay. I just want to check in the chat. Just give me a thumbs up if you understanding and following along with the whole idea here of the relative frequency and this experiment with the toast that I did. Nice. Got it. Well done, everybody. Good. Okay. So the thing with relative frequency is that we can use it to make predictions. So, and that's really what probability, a big part of probability is about, is being able to make predictions. So we can take this relative frequency and say, what if I drop my toast 500 times? Now, someone's already mentioned it's very messy, and I shouldn't be dropping my toast and all of that. So I really do not want to go and drop toast 500 times. It is not practical. It is not something I feel like doing. I don't have the time for it either. So what I'm going to do is I'm going to make a prediction, and I'm going to say 16 out of 25 times I found that it landed with the jam side up. So I'm going to times that. If I repeat that same experiment 500 times, then I just times those two numbers together, and I'll get 320. Okay, so relative frequency is very handy for making predictions like that, because the more we do an experiment, the more we repeat ourselves, the closer and closer we're actually going to get to these theoretical numbers. So we said it's a 50-50. We did the experiment. It came out at 64%. And now we can use that experiment and our findings from that experiment to make a prediction without having to actually go and do it many more times. Okay, so pop in the chat. What if I drop my toast 1,000 times? What is my prediction? What is my prediction for the number of times it's going to land with the jam side up? 640. Nice. Okay. Good stuff. Excellent. Now, let's look at this. Just to explain a little bit further, what is the probability of getting a 6 when rolling a dice? I think you all know that by now. We've been doing that quite a lot. Don't know where to ask how. We just take our relative frequency of 16 out of 25 and we times it by 1,000, and that gives me 640. Okay, so without having to actually go and do that, we can use the relative frequency to make a prediction. Right, so what is the probability of getting a 6 when rolling a dice? That is 1 out of 6. So a die is rolled 12 times. It lands on 6 1,900 times. What is the probability of getting a 6 in the experiment? The probability of getting a 6 in the experiment, we rolled it 12,000 times. We got a 6 1,900 times. So our probability is 1,900 over 12,000. So work out what that is and pop it in the chat. Check your answers, guys, that they make sense. 19 over 12 won't make sense as a probability. And we need to just also simplify. 19 over 120. And thanks for those who are putting it as a decimal. It's 0.16. And if we take 1 out of 6, that is also 0.17. Okay. So in this experiment where we rolled the dice 12,000 times, this is called the, sorry, I'm just going to change this. This is called the relative frequency. Okay, and then if I roll the die 15,000 times, what is the probability of getting a 6? So now we can use our probability, our relative frequency, to make a prediction. So 15,000 times by, what are we going to times by? Calculate this. If I roll the die 15 times, what is the probability of getting a 6? We need to times by our relative frequency, which we said was this number here, 0.16. That's at 2,400, I think is the right one. There we go. Okay. Okay, and just to be sure, this is the theoretical probability of getting a 6. When you do the experiment and you get a slightly different number, that is called the relative frequency. Okay. Okay, so now is your time to grab your coin. Okay, and we're basically going to do our own little experiment with our coin. And once you have your coin, you can quickly jot down this table or take a screenshot of the table. I want you to flip your coin 10 times and keep a tally of getting heads and tails. And then also write down the total, and yeah, just do that for now. Just keep it with you. Don't put it in the chat yet. Just hold your answer, and we will call for answers in due course. Now, do we know how to flip a coin? Not, guys, you just hold it like this and you flick it with your thumb, and the side of the coin that's got, I think all the coins have animals on them. Hey, Ms. Coco, the South African coins. Well, this is a 5 rand coin, so it's got a wildebeest on it. So that is heads. And then the other side with the coat of arms, that's tails. So if you know which is heads or tails, heads is where the animal is, and tails is where the coat of arms is for South Africa. Do it now, guys. Nice, Amachle. I can see you flipping your coin there. Everyone do it. Anyone else flipping coins? Okay, and then you keep your tally, heads or tails. Nice one, Mummy. Nice. Monica, that is my R. There she is, Miss Coco, giving us a hard time here. There is an R after A. Litakazi, just hold your answers, okay? Nice, Indepile. I see some coin flipping going on there. Shiraz, I don't know if I want to. I'm scared to hear about this experiment.
Was it toast? I have a feeling it had something to do with toast.
Okay. Right, looks like most people are done with their coin flipping. So please pop in the chat how many heads you got and how many tails. Five comma 5 is wrong.
I need to know how you can flip a coin 0.5 times. I need to know that.
There's some serious rigged coin flipping going on there. Okay, and you got to have a total of 10, okay? Between heads and tails, there got to be 10. And some of you are coming out so even with 5 and 5. I wonder how much coin flipping was going on there. Okay, so when I did it, not right now, but in the previous class, I got 4 heads, 6 tails. Okay, so what I want you to do now is also write down your probabilities. So we flip the coin 10 times. So let's do, let's do this. So we say this is 4 out of 10 and 6 out of 10. And then write that as a decimal and as a fraction. Oh, that's what I should also say. See, I am, you know how long I lived without knowing what heads and tails were. That's why I always feel it is my job to explain to people where the heads and tails are, just in case they're like me and don't know where heads and tails are. For the longest time, I didn't know. So don't feel bad. There are many of us who are like that. Okay, so 0.4 and 0.6 and 40% and 60%. Okay, so this is now your own little experiment with relative frequency, because the theoretical probability of getting heads or tails is the probability of getting heads. What did we say that was? That can only be 1 out of 2. And no jam involved in this one, because you know, jam that might skew the results and we could get fairly scientific. This is heads or tails. So these coins are 100% balanced, no one side favored over the other. So that's our theoretical probability. Compared to when we actually ran the experiment 10 times, we got not 50-50, but 4 out of 10. I got 2 out of 5 and 3 out of 5. So this is going to be my relative frequency for your experiment that you did with your coin flipping, as compared to the theoretical probability. So Bridget, that's what theoretical probability is. When we say, okay, listen everyone, if you're confused about theoretical probability and relative frequency. So theoretical probability is, technically speaking, we should get heads half the time, tails half the time. So when we tossed our coin, we should all technically have gotten 5 and 5. It should have come out like that. Theoretically speaking, that's what it should have been. But we did it, and all of us did it, and we all got different stuff. Some of us did get 5 and 5, half and half. Some of us got 30-70. Some of us got 60-40. And that difference, running this experiment, is called the relative frequency. So when you actually do it and you run the experiment and you do it a certain number of times, then your numbers are actually slightly different. But if you're going to go now and you do it many, many times, like thousands of times, it will actually start to go towards the theoretical probability. So you will start getting like half and half, heads, half tails. Okay, so it's just something that you have to, that we're going to work with today, is this idea of relative frequency, which is basically when you do experiments, the probabilities are just a bit different to what we are theoretically saying they should be. Shiraz got it 50-50. So that's interesting. Hers were the same, but mine were different. Most other people's were different as well. Kensani, if it is a coin, if it is a dice, it should be 1 out of 6 for each of the numbers. But if it is a coin, it is 50-50. That's theoretical. Yeah. Okay, so it all depends on what the situation is. There's going to be a theoretical probability, and then actually doing it in practice is going to give you something slightly different, but repeating it many times is going to make it come closer to what the theoretical probability is. Okay, can I get a thumbs up? Is everyone happy? Thumbs up in the chat if you are on board with relative frequency. Nice. Okay. Okay, let's do some practice questions with relative frequency. I just want to. Okay. Right. Here's another coin flipping experiment. So Josie wants to test a coin, test if a coin is biased. Does anyone know what biased means? What does biased means? Unfair. Yeah, unfair. Favoring, one-sided. Exactly. It's not fair. Favored to one side. Very nice. Sure. Watobians are not just good at maths, they're good at language as well. Excellent. Okay, so she flips the coin 30 times. Here are her results. Okay, not here results, but her results. Let's complete the relative frequency table. So in our relative frequency table, we're going to put the number of heads out of 30 and the number of tails out of 30. That's right. We got 22. And remember, we need to simplify. Watobians, I see you are not simplifying your fractions. 22 divided by 30 is 11 out of 15. And tails is 8 out of 30, which gives me 4 out of 15. Okay, so these are the simplified fractions, and you got to simplify your probabilities and your relative frequencies. Do you think the coin is biased? Explain in your answer. Pop in the chat. Do you think the coin is biased? Yes. Cecilia says yes. No. Give a reason. Yes, no, yes, no. What is what is your reason for saying yes or no? Does anyone want to volunteer an answer? Okay, so Isa says yes because it landed on heads way too many times. But like Ms. Coco said earlier, maybe it's got to do with the flipper. Whoever is flipping the coin. Yes, Sibonkuhle. You can unmute and ask or make your comment.
Hi, ma'am.
Hi.
I think it's not biased because it could be that she flipped the coin and it always landed on heads, or maybe the way she was flipping the coin and then it always landed on heads. I'm in between.
Yes, I think you're right. I think those are all good reasons. So if you're saying yes, it's just too strange that she gets so many heads, that's fine too. If you say no, because it could be completely random and it could be because of the person, that's fine too as well. Okay, so as long as you give a good reason. So Boitumelo says no, because logically coins can't be biased. Very true, very true. Manuel says no, because the coin isn't living. The coin is dead. Yes. Her flipping technique, yeah, we don't know. But as long as you give a good reason, guys, you'll definitely get a mark there. Right, so let's see who's been paying attention. Josie decides to flip the coin 150 times. Remember, she now wants to, so she basically wants to carry on checking and calculate an estimate of the number of times that the coin will land on tails. Some people are saying 40. Let's wait for some more answers. I'm not sure yet about the 40. 40. We're going to take that relative frequency of 4 out of 15 and we're going to times it by 150 and that's going to give us 40. Nice. I think everyone was paying nicely attention to what we were doing there. Well done. Okay, let's see something different. Yellow jelly beans. Okay. David and Becky want to estimate how many yellow jelly beans are in a tub of 500 jelly beans. A trial consists of taking a jelly bean at random, noting the color and replacing the jelly bean in the tub. Okay, so David goes 20 times. So that's what a trial is. So he sticks his hand in and taking a jelly bean, and then he gets 3 jelly beans. And then Becky does that 100 times and she gets 11 yellow jelly beans. Okay. Write down the relative frequency of David taking a yellow jelly bean. Pop it in the chat if you know. Come guys, let's get some more answers. And remember about that thing, even if you think you might, if it's wrong, it doesn't matter. No one's watching. Yeah. Okay. I agree with the 3 out of 20 because of this here and because of the relative frequency. Okay. He didn't, yes, there are 500 jelly beans, but he didn't he didn't try with all 500 jelly beans. He just did it 20 times. Okay. So 3 out of the 20 that he took were yellow. So that's why it's the relative frequency. It's not all of the jelly beans. It's not the 500. And I can see why some of you might have thought that it's the 500 as well, but it's only the 20. Okay, so now what is the relative frequency of Becky taking a yellow jelly bean? I think we can understand a bit better now. 11 out of 100. Yeah, so she took 100. She didn't take all 500. But she took 100, and that is 11 out of 100 for the yellow. Okay. Let's see if we can answer this question. Whose experiment gives the more reliable estimate of the number of yellow jelly beans in the tub? Give a reason for your answer. Becky, give us a reason. If you're saying it's Becky, give a reason. If you're saying it's David, give a reason. Yes, Becky, because she tried it more times. That's exactly it. Because the more you try something, the more accurate your result is going to be. I'm just going to write here briefly more times. Okay, nice. Okay, let's see. Let's do one more. Let's do this one. A spinner has 4 sections, each labeled A, B, C, and D. Susan and Helen spins the spinner a number of times. The table shows some information. Okay, so there's Susan. Number of times she spins, it's 20. Helen is 120. Okay, let's see if you can complete the table. I'll give you a few more minutes to read. Pop your answers in the chat, everybody, as soon as you're ready. Yes, I agree with your 0,4. That is 8/20, which simplifies to 0,4, or 8/20 is 2/5. Okay, and now for Helen, she did 120 spins. So what number of bees did she get? So working backwards, some of you have answered that already. Nice. 42. I wonder if someone wants to tell us how they got it. Any volunteers? Yes, Yenzi.
Hi, ma'am. What
Hi
I
there.
did was I said, as I said, that's 0,35, and then I times it by 120.
Excellent. Yes, that's perfect. That gives me 42. So that's just working backwards. Okay. And that's it, I think, for that question. Yeah. Okay, well done. Let's do one more from, let's see. Let's see if we can find something a little bit interesting. Okay, here we go. Okay, so the sides of a spinner are labeled 1, 2, 3, and 4. The spinner is biased. The probability that the spinner will land on each of the numbers 2 and 3 is given in the table. The probability that the spinner will land on 1 is equal to the probability that it will land on 4. So work out the value of x. Yoria, that was quick. Let's give more people a chance to just read the question and to also have it a think. If you're not sure, just read the question again, and remember, I'll give a hint. Probability, all probabilities can only add up to 1. So the probability can only be, the probabilities of all of these added together can only be 1. Okay, so the probability that the spinner will land on 1 is equal to the probability that it will land on 4. So this is 0,5. So we are short 0,5. So this must be 0,25 and 0,25. Nice on Amika writing that whole calculation for us. Beautiful. Nice. Okay, so that is 0,25 for x. And then Sarah is going to spin the spinner 200 times, work out an estimate for the number of times it will land on 2. So make your prediction. What will it be if she spins it 200 times? Nice. Masood and Akunele Ntokozo. Well done, everybody. I see some answers coming in. Good stuff. We're just going to take the 0,3 and times it by the 200. And that's going to give me 60. Okay, that is it from my side for this evening. Miss Coco, I think it is time for the quiz. So thank you so much, everyone. I hope you enjoyed tossing your coin and doing your probability experiments. And I'll see you back here again on Tuesday when we do Venn diagrams. Wonderful. Have a good weekend. Bye-bye.